Hi!
We're Team ARTEMIS, a final year MEng project from the University of Manchester.
ARTEMIS stands for Autonomous Robotic Technology Enabling Minimally Invasive Surgery. The aim of this project is to explore the technological challenges within the field of biomedical engineering and minimally invasive surgery.
Post-operative surgical infections exist in over 100,000 surgical cases per year and cost the NHS over £930 million per annum.
Minimally invasive surgery reduces the number of surgical incisions to a single entry, which reduces patient scarring, infection and hemorrhaging.
Our goal is to deliver a scaled prototype surgical device, focusing on the main categories of communications, power harvesting, biomedical sensors and data control.
The project runs in collaboration with a team of 5 medical and mechatronic engineers from the University of Leeds. Our project is sponsored by National Instruments, who are providing equipment and advice throughout the project.
The team from Manchester is focusing on the electronic components of the project, and the team from Leeds focusing on the micro-miniature mechatronic components.
The project vision allows for a selection of different use cases to be swallowed by the patient. This will connect to an external base station which will incorporate wireless power transfer. Uploading various internal data to a web server allows the clinician and patient to view the real-time capsule status on any web-enabled device. The aim of the project is to integrate the contributions from both universities for a gastric balloon use case. Motivated by the advice of surgical specialists, the device is swallowed along with a quantity of water which inflates a gastric balloon and regulates its size over time within the patient's stomach.
Hello, the project is divided into 4 sub-teams and we are the sensor sub-team. We are exploring the implementation of biomedical and inertial sensing within the capsule.
In order to monitor the surrounding capsule environment and measure the temperature and capsule orientation within the biological surroundings, we are working on a sensor interface allowing different sensors and actuators to be monitored and controlled within the system through a simplified interface. Our challenge is to create a sensor interface which can support the widest possible range of sensors and actuators within a low power environment.
Hello, we are the communications sub-team.
Our focus was to provide a bi-directional 3-body wireless link in order to send sensor data from the capsule to the base station and control commands from the base station back to the capsule. This had its challenges as we had to transmit through human tissue, therefore the frequency had to be chosen which would provide minimum attenuation. When transmitting data, we also needed to find the optimum modulation scheme for through-tissue communications at the frequency chosen, in terms of bit error rate, capacity and power consumption.
Hello, we're the power sub-team and we're focusing on providing the power to the capsule inside the body.
The conventional method of providing power to the electronics is through silver oxide batteries for biomedical applications. However, we're looking at the possibility of wireless power transfer for longer duration inside the body, which would exceed the lifetime of traditional batteries.
The energy levels must also be managed and monitored within the capsule to ensure that the system has sufficient power to perform all of its operations.
Hello, I'm working on the base station. The base station is a way of receiving all of the data on the outside of the patient and processing this into useful information that can be interpreted by the patient and the clinician for monitoring and diagnosis. I'm focusing on receiving the wireless data from the communications team and then processing this data to upload onto a web server that the patient can see all of the relevant information on their mobile devices, as well as the clinician who can control the capsule operations and make the informed diagnosis.
So far, you have heard about all the challenges of the individual sub-teams, but the biggest challenge was to integrate all components together into one functional prototype. In collaboration with the team at the University of Leeds, we have developed a 3D CAD model of the capsule enclosure to layered electronic and mechanical design. The result is a 3D printed capsule enclosure at a 6:1 scale, equipped with custom-made PCB of a professional standard. As you can see, arranging the PCBs has been quite a challenge to ensure that everything fits together and operates as expected.
Thank you for watching our team video. We hope you've enjoyed learning all about the different challenges and discoveries of the project. If you want to find out more information about the project, please visit our website or contact us directly via our email.